Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 17, part 1. In this lecture, we will be solving one numerical question based on vapor absorption refrigeration system. So, the working fluid which is used is the water lithium bromide system. There are two types of working fluids which are used. One is water lithium bromide, another one is the ammonia water system. In the previous lecture, we have discussed about the construction, the working principle of ammonia water absorption system as well as water lithium bromide absorption system. So, this numerical question will be based on water lithium bromide system. A single stage water lithium bromide vapor absorption system, cooling system operates at an evaporator and a condenser temperature of 2 degrees centigrade and 40 degrees centigrade. So, the evaporator temperature is 2 degrees centigrade and condenser temperature is 40 degrees centigrade. The temperature of absorber and generator are 33 degrees centigrade and 90 degrees centigrade. So, absorber temperature and generator temperature is given. So, after reading the problem completely, I will write the given data, then we will solve the problem. The solution heat exchanger has an effectiveness of 65% and the mass split of the weak solution is 0.05 kg per second. Assuming the condition of refrigerant at the outlet of the evaporator and condenser to be saturated, determine the coefficient of performance of the system. So, before writing the given data, let us have a quick recap on the construction of this water lithium bromide absorption system. There is only one difference between water lithium bromide absorption system and ammonia water system. In case of ammonia water absorption system, a rectifier is used. The refrigerant vapor which is leaving the generator has some absorbent carryover, that is water carryover, which is purified, rectified in the rectifier, and the pure vapor, even the pure vapor is not 100% concentration, it is 99.9%. So, in case of water lithium bromide system, there is no rectifier. The vapor, water is the refrigerant, so the vapor, water vapor which is coming from the generator, which is generated from the generator, does not carry any lithium bromide. So, it goes directly to the condenser without there is a requirement of rectifier. So, here 1, 2, 3 is the weak solution circuit, 4, 5, 6 is a strong solution circuit, 7, 8, 9, 10 refers to the refrigeration circuit. So, it is quite a lengthier problem. So, I will be solving in two parts, part 1 and part 2. So, let us write the given data. The working fluid is water lithium bromide. Let us absorber temperature is given as 33. Absorber and generator temperatures are 33 degrees centigrade and 90 degrees centigrade. Temperature of absorber is 33 degrees centigrade. Temperature of condenser is 40 degrees centigrade. Temperature of generator is 90 degrees centigrade. Anyway, I have given a detailed solution in the PPT. It will be easy as I explain and write so that the learners can understand easily. So, the evaporator temperature is 2 degrees centigrade. Effectiveness is represented by the symbol effectiveness of the solution heat exchanger. Effectiveness of the solution heat exchanger. SHX stands for solution heat exchanger. You can see in the diagram also. This is the solution heat exchanger. Solution heat exchanger. So A stands for absorber, G stands for generator, SP stands for solution pump, PRV pressure reducing valve, C stands for condenser, V is expansion valve, and E is evaporator. And one more data is given, mass flow rate of the weak solution 0.05 kg per second. So due to system compatibility, the m dot is not visible. So wherever m is there, it should be m dot. So m dot is m dot ws. Weak solution is represented by the subscript ws. Strong solution is represented by the subscript ss. So before writing the flow rate, effectiveness of the solution heat exchanger is given as 65%, which is equal to 0.65. And mass flow rate of the weak solution is equal to 0.05 kg per second. So these are all the given data. We need to find out the COP of the system. COP of the system. So 4 temperatures are given. That is the temperature of absorber, generator, condenser, and evaporator. So using the evaporator temperature and the condenser temperature, we can find the low pressure and the high pressure. That is the evaporator pressure and condenser pressure. So let us solve this problem. So the refrigerant is water and absorbent is the lithium bromide. So I will be using steam tables to find out the pressure value, and to find the concentration, I will be using the pressure, temperature, concentration chart, PTX chart, and for enthalpy, I will be using HTX chart, enthalpy, temperature, concentration chart. So first one is from steam table. From steam tables, at TE is equal to 2 degrees centigrade, the corresponding pressure I will write. Similarly, at TC is equal to 40 degrees centigrade, what is the condenser pressure? So let us go to the steam table. So here this is the temperature values are given, and this is the pressure value. So corresponding to 2 degrees centigrade, so you have to use table 1 in the steam table, where the first column is temperature and the second column is pressure, and of course specific volume, specific enthalpy, and specific entropy are given in the third, fourth, and fifth columns. So corresponding to 2 degrees centigrade, the pressure is 0.00706 bar. It is given in bar. The unit of the pressure in the table, it is given in bar, 0.00706. See here, 0.00706 bar, which can be converted into kilopascal. 0.00706 bar, which is equal to 0.706 kilopascal. Similarly, the condenser pressure can be found corresponding to 40 degrees centigrade. This is from the first page from 0 to 19. So next one is 40. 40 is here. What is it? Again, this is temperature. This one is pressure. So corresponding to 40, the value is 0.07375. 0.07375. 0.07375 bar. So if you convert into kilopascal, it will be 7.37 kilopascal. 7.375. So that is 0.07375 bar converted into kilopascal. So these two values. So the first step in while solving the numerical question in vapor absorption system is the temperatures will be given. First we need to find out the evaporator pressure and condenser pressure. 7.375. Anyway, I have just written for two places. Let me write it 7.375 kilopascal. Next step is to find determining the concentration of the weak solution and the concentration of the strong solution. Concentration of the weak solution and concentration of the strong solution. So, next one is finding the concentration of weak solution and strong solution. Strong solution. Finding the concentration of weak solution and strong solution. Weak solution concentration is or mass fraction is represented by the letter capital X. Ws stands for weak solution and SS stands for strong solution. So it's a function of evaporator pressure and absorber temperature. Of course, evaporator pressure and absorber pressure will be the same theoretically in ideal condition, and condenser pressure and generator pressure will be same. So it's a function of evaporator pressure. We know the value of evaporator pressure. We know the absorber temperature is given. So using PTX chart, so this is equal to, let us go to the chart. This is the PTX chart. If you know any two properties, we can find the third property. If you know pressure and temperature, we can find concentration. If you know pressure and concentration, we can find temperature. This is solution temperature. This is solution temperature T. This is saturation pressure. And these are all X. These are all X value. And these inclined lines are the X value. Okay. So the pressure is given here, it is in kilopascal. That's why I have converted the bar, the pressure which was taken from the steam table, which is in bar, it was converted into kilopascal. So this is in kilopascal. So if you see, so at PE is equal to 0.706 kilopascal and temperature of absorber is TA is equal to 33 degrees centigrade. From PTX chart, the concentration of the weak solution is equal to, let us go to the chart. See here, this is the solution temperature. So here we have to find out 33 degree comes here. This is 33. Pressure is 0.07. So it will come somewhere else here. So this is 1 kilopascal and somewhere else it comes to 0.07 kilopascal. So you have to find out the intersection point. So this is the concentration. These are all X values. These are all X values, concentration values. We have to use the same. We have to use the same chart for finding concentration of the weak solution as well as concentration of the strong solution. So you can find this is 33 degrees centigrade and this is 0.07 kilopascal. Maybe in the video the value, the chart, the intersection point may not be clear, but you can take the PTX, download the chart PTX and HTX chart, and you can compare the values. So if you see this one, the interest, it will come around between 50 to 60%. That is almost at the midpoint, which is about 55%. Okay, so this is the intersection point. This is the intersection point. So the concentration of the weak solution, it comes to 0.56, 0.56. And if you see this one, so this is, that is 56% the absorbent, and the remaining 44% is refrigerant. Here again, let me emphasize, weak solution is weak in absorbent, strong in refrigerant. And here in a water lithium bromide system, we are defining weak solution as weak in absorbent and strong in refrigerant. Strong solution is strong in absorbent, weak in refrigerant. So this comes to 0.56, this one. Similarly, we can find the concentration of the strong solution. Concentration of the strong solution is concentration of the strong solution, it is a function of condenser pressure, which we have found from the steam table, and generator temperature. That means at condenser pressure is 7.375 kilopascal. 7.375 kilopascal, and generator temperature is equal to 90 degrees centigrade. From PTX chart, concentration of the strong solution is equal to, again you have to use the same chart. 90 degree will come here. This is 90 degree, and the pressure is around 7.3 kilopascal, so that will come somewhere else here. This is 7.3 kilopascal, and you have to find out the intersection point. So it will come somewhere else here, somewhere else here. Please download the chart and take the printout and use scale pencil to find out the intersection point exactly, and this will give the strong solution concentration. So the strong solution concentration comes to around, that is 62% or 0.62. That means it is strong in absorbent, weak in refrigerant. 62% absorbent lithium bromide, and remaining 38% is refrigerant. So the first step is to find out the evaporator pressure and condenser pressure. Step number 2 is finding the concentration of the strong solution and weak solution. Using these two concentration, we can find the circulation ratio. Once we find the circulation ratio, we can find out the mass flow rate of the strong solution and the mass flow rate of the refrigerant, because mass flow rate of the weak solution is given in the problem. The next one is circulation ratio. Circulation ratio, that is CR. So let us go to the solution which is given in the PPT. See, again, for the reference, I have given a detailed solution in the PPT. From PTX chart, if you, this is the strong weak solution concentration. This is the strong solution concentration. So next I will be calculating the circulation ratio. So the formula is CR refers to circulation ratio, concentration of the strong solution divided by the difference between the concentration of the strong solution and concentration of the weak solution. Strong solution, this is 0.62 divided by 0.62 minus 0.56. So if you calculate, you will get the circulation ratio comes to 10.33. 10.33. If you see the given data, mass flow of the weak solution is given, but the mass flow of the strong solution and refrigerant is unknown, which we have to determine. So let me change this slide. The value is coming in the next one. So let me stretch this one. I think now it's okay. So here also everything will be m dot. It is not m, it is m dot. So the mass flow rate of the weak solution can be determined using this formula, circulation ratio multiplied by m dot r. Mass flow rate of weak solution, MWS is equal to circulation ratio into m dot r. Sorry, using this we can find out the mass flow rate of the refrigerant. So this mass flow rate, this is the standard formula. This is given in the question. This we have calculated. So we can find m dot r. Using this formula, we can find m dot r is equal to m dot ws divided by cr. So this is given in the question, and circulation ratio we have found out. So this is equal to m dot ws. This is given as 0.05 divided by 10.33. So this is equal to m dot r is equal to 0.00484 kg per second. So m dot r is m dot ws by cr. So m dot r, the refrigerant mass flow rate is 0.00484 kg per second. So how to find the mass flow rate of the strong solution? Circulation ratio minus 1. There are two formulas. So actually, if you see this one, mass flow rate of the strong solution, from this solution only some portion of in the generator, as the solution is heated by the external source, at one point of time the refrigerant vapor evolves, and the weak solution becomes strong solution, and the refrigerant vapor goes. So there is a mass balance in the generator. M3 is equal to M4 plus M7. If you see the diagram, so this is the entering solution, this is the leaving solution. So this will be equal to this is entering solution will be equal to the summation of M4 and M7. So let us calculate here I will write the mass flow rate of the strong solution. Mass flow rate of the strong solution is equal to circulation ratio minus 1 into m dot r into m dot. Circulation ratio is known. So this is equal to 10.33 minus 1 multiplied by m dot r we have calculated here. So it's 0.00484. So that is m dot ss is equal to, this is m dot ss is equal to 0.04516. 0.04516. .04516 kg per second. So this is the mass flow rate of this one. So that means the pumping solution has a mass flow rate of 0.05 kg per second, out of which this much amount 0.00484 kg per second of refrigerant has been converted into vapor, and the remaining is the mass flow of the strong solution, which is leaving the generator. So that is mass flow of the weak solution is equal to mass flow of the strong solution plus m dot r. Using this formula also we can find out mass flow of the strong solution. This is another formula which I have given. So that's what we have calculated, 0.04516 kg per second. 0.04516 kg per second. So I will stop this lecture at this point. We will be continuing this problem in the part 2 of this lecture. Thank you.